When you learn trigonometry in an algebra or pre-calculus class, you usually are thinking about right triangles. So katoa. And I don't want you to forget about what you learned about right triangles. But in this class, trigonometry is more important for the graphical properties of sine and cosine, to model oscillatory behavior. And that ultimately is really what trigonometry is more useful for in the big scheme of things. Yes, we love applying it to triangles, but more importantly, it's for modeling oscillations, even complicated oscillations that come up in signal processing. It's important to get the graphs of cosine and sine right, and maybe even feel comfortable drawing those graphs and thinking about special values without technology. To start with, you want to think about the unit circle. That's the circle in the plane, say the XY plane, centered at the origin with a radius of 1. Centered at the origin with a radius of 1. Like that. And if it's a radius of 1, that's 1, that's 1 on the y-axis. This is -1 on the x-axis, and this is -1 on the y-axis. There's the unit circle in the plane. It is important that you remember it has equation x squared plus y squared equals 1. The reason it has that equation is because of the Pythagorean theorem. Given any point in the circle, you can draw, like say right here, you can draw a right triangle in the picture like this. The x coordinate of the point and the y coordinate of the point are these distances that are labeled. And the hypotenuse of the right triangle has a length of 1. The Pythagorean theorem would say x squared plus y squared equals 1 squared. Well, 1 squared is 1, so we can just write a 1 there. I like describing how to figure out the graphs of cosine and sine in terms of a smart bug called TrigBug. Okay, pretend I've got TrigBug between my fingers here. TrigBug is a very smart bug. I'm being very gentle with TrigBug. Well, I could let him fly around. Maybe I should let him free. But TrigBug, every time TrigBug sees the unit circle, he really wants to land right there at the point 1, 0. And then if I give TrigBug directions, if I give TrigBug a number, TrigBug will travel around the unit circle a distance equal to the absolute value of the number that I give TrigBug. Now, what is the circumference of the unit circle? I hope you remember that it's 2 pi, right? The circumference of a circle is pi times the diameter, 2 pi times the radius. The radius of the circle is 1, and therefore the circumference is 2 pi. So if I give TrigBug the number, and 2 pi is about 6.28. If I give TrigBug the number 2, say, here, TrigBug, here's the number 2. TrigBug will walk around the unit circle counterclockwise, because 2 is positive, 2 units of distance. Now, if it's 2 pi units around the unit circle, that means it's pi units half the way around the unit circle, about 3.14, and pi over 2 units 1/4 of the way around the circle, about 0.7, or no, 1.57. 2 would bring you into the second quadrant over here. Maybe right around here or so would be 2 units of distance. The first coordinate of that point, by definition, is the cosine of 2. And the second coordinate of that point, by definition, is the sine of 2. And TrigBug is so smart, TrigBug can estimate what those are. Maybe TrigBug's smarter than me and can estimate it without a calculator. I'm going to use a calculator. It does look like the first coordinate of that point should be somewhere around -0.2 or -0.3. Is that indeed what the cosine of 2 is? Make sure you're in radian mode. Yes, I'm in radian mode, not degree mode. Cosine of 2, negative 0.4. Negative 0.42 more approximately, more accurately. And sine of 2 is going to be the second coordinate of that point, maybe 0.8 or so. Sine of 2 is, well, 0.9 or so, 0.91. But wait a minute. How is this related to things like radian measure of angles? If I draw an angle by looking at two rays, one of which points directly to the right, effectively it's the positive x-axis, and one of which points from the origin through this point, this angle is said to have a radian measure equal to this length of 2 units. The radian measure of this angle is 2. You can relate this to angles, is what the point I'm trying to make. How do you figure out what it is in degrees? It should be somewhere between 90 and 180 degrees. The key thing is that 2 pi radians equals 360 degrees. Divide both sides by 2. That says pi radians is 180 degrees. And that fact allows you to write down a conversion factor. If I want to take an angle of 2 radians and convert it to degrees, I need to multiply by a factor whose units are degrees per radian so that the radians cancel. Degrees per radian, divide both sides of this equation by pi radians. 180 degrees per pi radians. Kind of a weird angle, isn't it? It's going to be 360 over pi degrees. Whoa, that's weird, but it's still valid. Should be a bit bigger than 90. 360 divided by pi is 114.6 degrees approximately. Don't be bothered by the fact that in this weird example, there's a pi in there in the degrees. It is a weird example, but this is correct. Yeah, it looks all right. 114.6 degrees doesn't look too far off, right? If going through the first quadrant is 90 degrees, we're just a little bit past that. Okay, yeah, more typically, we don't use whole number radian values. More typically, we focus on special radian values that do involve pi. You know, in terms of degrees, that the most common angles people typically think of is 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees, 145 degrees, 100, let's see. Oh, no, I meant something different here. 135 degrees, 135 degrees, 150 degrees, 180 degrees. We can convert all these to radians by using the opposite conversion factor. Take this fraction right there and flip it over. This one's 180 degrees per pi radians. If I flip it, it's pi radians per 180 degrees. So for example, with 30 degrees, if I multiply that pi radians over 180 degrees, the degrees cancel. It's okay to use a circle or a DEG. Giving me 30 pi over 180 radians, which simplifies to pi over 6 radians. 30 degrees is pi over 6 radians. 45 degrees turns out to be pi over 4 radians. 60 degrees is pi over 3 radians. 90 degrees is pi over 2 radians. 2 pi divided by 4, 2 pi units, or radian measure of 2 pi all the way around the unit circle. A quarter of that would be pi over 2. 120 degrees, take pi over 2 and add another pi over 6 to it. By getting a common denominator of 6, you'll get 4 pi over 6, which simplifies to 2 pi over 3. Yes, this is pi over 2 plus pi over 3. 90 degrees plus, oops, I meant pi over 6, sorry. 90 degrees plus 30 degrees. Getting a common denominator of 6 gives me that. That simplifies to 4 pi over 6, which simplifies to 2 pi over 3. This one's 3 pi over 4. This one's 5 pi over 6. And this one, 180 degrees, is pi. All in radians here. Etc. You should be able to, if you have enough time, do other kinds of conversions. Probably should do the next one since that's the CP. 210 degrees is 7 pi over 6 radians. You should be able to convert 7 pi over 6 radians to 210 degrees. You can go backwards as well. You can talk about negative angles, for example, with the class participation, negative 300 degrees. If it helps you think about the picture, the angle would be going clockwise. There's 180 degrees, and there's negative 270. You'd be a little bit past negative 270 degrees. It would be equivalent to pi over 3 radians if I went counterclockwise. If I want to figure this out, I could figure it out as negative 2 pi plus pi over 3. That would be one way to do it, or you can use the conversion factor. Getting a common denominator of 3, this would be negative 6 pi over 3 plus pi over 3. This would be negative 5 pi over 3. Should have been what you got with the class participation problem there. Very quickly through this, right? This is something you should have seen before, and you're just trying to remember. How is this related to what I said was the most important thing? The graphs of cosine and sine. Go back to the unit circle, and instead of imagining particular angles like 2 radians or something else, imagine that it's a variable number of radians. You could call it theta. You could think of it as an angle. More commonly for our applications, though, we're going to call it t, because it's going to represent time. As t radians varies, as trig bug walks counterclockwise around the unit circle, starting from the point 1, 0 at t equals 0, how do the first and second coordinates vary? Focus on the first coordinate first, the cosine. It starts out at 1 when t is 0. And because you're moving to the left, it's got to go down and have a value of 0 when t is pi over 2, about 1.57 for t. And have a value of negative 1 when t is pi, 3.14 approximately. Back up to 0 when t is 3 pi over 2. And then back up to 1 when t is 2 pi. That defines the basic cycle of the cosine. Watch my finger here. Down, then back up, like that. And then it repeats as you continue around the unit circle. It also goes backwards in time, so to speak, if you let t be negative and let trig bug walk clockwise instead of counterclockwise. How about the sine? That's the second coordinate. When t is 0, that starts out at 0. Because trig bug is walking upwards, y is increasing. The graph of sine starts going upward, has positive values, until it reaches a maximum of 1 when t is pi over 2. Back down to 0 when t is pi, negative after that, reaching negative 1 once t is 3 pi over 2. Sine is the second coordinate. Then back up to 0 when t is 2 pi. So that's a very quick way of saying what these graphs should look like, and now I'm going to draw them. Not perfectly. Nobody can draw these things perfectly, but I'll do my best. in the time that I have. Let's make cosine be red. Starts up at 1 when t is 0. This is going to be a t-axis. In the original picture, I labeled the axes x and y. In this picture, I'm labeling the horizontal axis with a t. What should I label the vertical axis? Probably nothing is what's best. Or, well, okay, maybe I'll do, since cosine is the first coordinate, I'll do an x in red, and the cosine graph's going to be red. And since sine is the y coordinate, I'll do a different color for sine, say green. This axis represents both letters, is what I'm trying to say. It represents the x coordinate of trig bug in the original picture for the red graph, and the y coordinate of trig bug in the original picture for the green graph. The red graph's going to be the graph of cosine. It goes down, then back up again. And it continues. But of course, you can't draw it forever. It's only in your imagination that it continues forever. Over here, it goes, it's periodic as well. It does the same kind of oscillation. This is going to be the graph of x equals cosine of t. And I'm literally going to call it an x here for the output instead of a y, because it does correspond to the x coordinate in the original picture. The graph of sine starts out at 0 when t is 0. Goes up. Trig bug is traveling upward in the original picture. Reaches a maximum of 1 at pi/2 radians, where x reaches 0. Right? When you're at the top of the unit circle, y is 1 and x is 0. So the green graph is going to have to reach its peak at the same spot that the red graph has a 0 there. Then you're going to go down. The y coordinate's going to be 0 at pi. Same spot where the red graph, the cosine graph, has a minimum. When we're at this point, pi radians. X is a minimum, -1, y is 0. These points have to match up. Continue. You got to be at a minimum at this point. And then at 0 at this one, etc. What are some specific points on these graphs? Yeah, this graph is the graph of y equals sine t. Don't be bothered by the fact that the outputs of these functions are being labeled with different letters. Okay, it's a convenient thing. Don't be bothered by the fact that this vertical axis has 2 letters. It's just a convenient thing. I could draw 2 separate graphs if I wanted to, but as long as I keep it straight in my mind that the red graph has an output labeled x based on the original picture, and the y, and the green graph has an output labeled y based on the original picture, that's a helpful thing. What are some particular points? Pi/6, 30 degrees is a special angle. That point has coordinates pi/6, 1/2, it turns out. That's a 1/2 there. Sine of pi/6 is 1/2. How about the cosine of pi/6? It's the second coordinate of that point. First coordinate is still pi/6. Second coordinate turns out to be square root of 3/2. Square root of 3/2. This bringing back memories. It's about 0.866. Where these two graphs meet, when t is pi/4, red and green make purple? No, but here it does. The coordinates of that point are pi over 4, comma, square root of 2 over 2. The cosine and sine of pi over 4 are equal. Square root of 2 over 2. Why? They have to be equal at 45 degrees because you're on the line y equals x there in the plane. The coordinates are the same there, and they both turn out to be square root of 2 over 2, which you can check by the Pythagorean theorem. By the way, it's okay to write square root of 2 over 2 as 1 over square root of 2 as well. And you can leave your answer like that. You don't have to rationalize the denominator. What? My teacher said, always rationalize the denominator. No, you don't have to. It's not like dividing by 0. It's nice to sometimes because it helps the grader check your answer. Everybody should get the same answer when they rationalize. And it's also a helpful technique, especially for computing limits, as we will shortly see next week, to rationalize the denominator. But here, you don't have to. You could write the cosine and sine of pi over 4 radians as 1 over square root of 2. It's okay. At pi over 3 radians, that's pi over 3 radians. This point has coordinates pi over 3 comma 1/2. The cosine of pi over 3 is 1/2. And this point has coordinates pi over 3 comma square root of 3 over 2. Sine of pi over 3 is square root of 3 over 2. And you could continue finding lots of other special values, including when the graphs go negative. For sake of time, I'm not going to. But you should feel comfortable working at doing that. What's most important for our purposes is taking these basic graphs and using them along with transformations of graphs like horizontal vertical shifts, vertical compressions and stretches, horizontal compressions and stretches, and using them to model oscillatory behavior. This is the most important thing for us right now. Maybe have time for a couple examples here. Let's say we have a graph that looks like this. And it does continue on forever like that. It's periodic. And let's say we know this point is the point 0, 7. And let's say this point right there is the point, let's make it be 3, 3. And the goal is to find a formula for this function. Find a function whose graph looks like this. Okay. You want to use trigonometry. You want to use either a cosine or sine because it's oscillating. What kind of information do you need to be able to figure out what this function is? First of all, you need something called the amplitude. The amplitude can be thought of as the vertical distance between a line midway through this kind of graph with an output of 7 in this case, and say the lowest point or the distance between that and the highest point, vertically speaking. You can see that distance is 4, right? 7 minus 3. Look at the second coordinate, 7 minus 3. If this second coordinate was a 2, it would be 7 minus 2. That means this distance is 4 as well, which also implies that this point up here is 7 plus 4 for the second coordinate, 11. Also by symmetry, since this distance right here is 3, this distance right here should also be 3, so the first coordinate should be 6. Oh, no, excuse me. I did the wrong thing. Sorry. That distance should be 3 times 2. 6. So this coordinate should be 9. It's this distance right here that should be 3. Okay, easy to get confused. This distance right here is also going to be 3. This point has got to have coordinates 12, 7. So the amplitude is 4. By symmetry, I was able to figure out other important points' coordinates. And I can now also figure out the wavelength or period of this graph. Maybe it would be helpful to find one more point. This point right here. I continue to the right by 3 and down by 4. This point is going to have coordinates 15, 3. The wavelength or period is the horizontal distance between these points. Most typically in this class, we're going to call it a period and label it with a capital T, because most of our applications, the horizontal axis is time. But you should realize in physics classes, if you have a graph like this where the horizontal axis is a distance, then you'd more likely call that a wavelength. A horizontal distance between the low points. You could also say it's a horizontal distance between the high points, like these 2 points here. It's one cycle. You could say it's the horizontal distance between these 2 points too, because that's one cycle of the wave. And what is it? It's 15 minus 3. It's 12. T, the period, is 12 in this case. If time is in seconds, say, then the periods would be in seconds. If the horizontal axis was a distance in meters, then the wavelength would be in meters. A, the amplitude, is that distance there. It's 4. What are its units? I didn't say what the units for the vertical axis would be. It depends on the application. Maybe the horizontal axis is a time, and maybe the vertical axis is a distance, maybe like a bob floating up and down in the water. Then maybe the vertical axis is a distance in like centimeters or inches or something as the bob goes up and down. What should I call the vertical axis? I'll go ahead and call the vertical axis y here. But just because I'm calling it a y does not mean I should necessarily use a sine function like I did in the previous page. Maybe a cosine function would be easier, but the fact that this graph starts out at its midline value of 7, that's average of the extremes of 11 and 3 for the output. 7 is the average of 11 and 3. And it starts out there and goes down. It's going to be best to use a sign with a negative sign in front of it. And I just used the word sign in 2 different ways there. It's going to be best to use the sine function, sin, with a negative sign in front of it, sign. Because it's starting at the midline, sine is easiest. Because it's going down, we need a negative sign in front of it. So we write negative the amplitude times sine of something times t. And then we also have to take one other thing into account. The fact that this thing is centered at a horizontal line at 7, y equals 7 instead of 0, as the original sine graph was. That corresponds to a vertical translation. I need to add 7 to this. But the question is, what goes there? The sine and cosine graphs that I originally drew based on the unit circle had periods, wavelengths of 2 pi, because that's how far it took trig bug to go around the unit circle. Here, the period is 12. So whatever I put in here in place of the question mark needs to be something that is t goes from 0 to 12, not, and also 3 to 15. I go through one cycle. Question mark times t needs to equal 2 pi when t is 12. That's an algebra equation to solve for question mark. That means question mark is 2 pi over 12. Pi over 6. In general, question mark is 2 pi over the period. Period typically labeled capital T. Again, in this case, that's 12. 2 pi over 12 simplifies to pi over 6. Okay. This is going to go through one period now as t goes from 0 to 12. Because the input being multiplied by pi over 6 will go from 0 to pi over 6 times 12, which is 2 pi. You can always check it. Go to your graphing menu, clear other things out here. -4 sine of pi over 6 times x. Pick a good window like the one that I drew by hand. Say x goes from 0 to 20 and y goes from 0 to 12 or something. Maybe I'll also draw a horizontal line in at 7. And see both of those graphs. Whoops. I forgot something, didn't I? I forgot to add 7. I forgot to add 7. Plus 7. Okay, regraph it. There it is. And we are going through one period as t goes from 0 to 12. This is a 12 right there. Okay, and there's the line y equals 7. Yes, we're running low on time. Technically, you should also be able to handle horizontal translations of these things. That gets tricky. Like if I added 1 to all these first coordinates, made my y-axis over here, I'd get the same formula, except I'd have to replace t with t minus 1, corresponding to a rightward shift by 1 unit. And I'd have a pi over 6 times t minus 1 inside the parentheses, which you can multiply the pi over 6 through, could look like that for the input of the sign, if it was a rightward shift by 1 unit. If I start at the peak or at the lowest point when t is 0, if I'm up here and I go down first before oscillating, or if I'm down here and go up first before oscillating, it's best to use a cosine instead of a sine. Possibly with a plus sign in front, possibly with a minus sign in front. I think what would be best to do for our last 7 minutes here is to talk about solving trigonometric equations. Like if this is modeling a bob floating on the water, going up and down as time goes by, I might wonder, when does the bob have a height of 10? It would have a height of 10 at, technically speaking, according to the model, infinitely many values of t, because the graph goes on forever and ever in both directions. That horizontal line at 10 is going to cross this green graph infinitely many times. I just want one answer, though. That'll be good enough. So I'm really wondering, when does this function equal 10? What's one value of t where it equals 10? So it's a matter of taking that function, -4 sine of pi over 6 times t plus 7, and setting it equal to 10 and solving for t. You do that by trying to first isolate sine of whatever's inside its parentheses on one side by itself, and then using the inverse sine or arc sine function. But that will only give you one possible answer, not every answer. So I'll start by subtracting 7 from both sides and get -4 sine of pi over 6t equals 3. Then I'll divide both sides by -4 sine of pi over 6t equals -3/4. Is -3/4 a special output of the sine function where I could figure out the answer exactly here? No, it's not. I need technology. I can represent the answer exactly in terms of the inverse sine, also called the arc sine function. And I will do that here, but ultimately I am going to have to approximate it with technology. So yeah, take the inverse sine of both sides. I haven't said what the inverse sine function really is yet. I will hopefully have time for that, even though we only have 5 minutes left in class. Being the inverse function of sine, these cancel, so to speak. Under function composition, they're inverses. They go away. To finish solving for t now, multiply both sides by 6 over pi so that the pi over 6 goes away. Looks like one answer for t is 6 over pi times the inverse sine of -3/4. Of course, that doesn't have a ton of meaning to you unless you approximate it. Making sure you're in radian mode. We pretty much stay in radian mode unless told otherwise. First, take the inverse sine. I need the second function button. And then press the sine button. There's inverse sine of -3/4. I also could have typed -0.75. Multiply that by 6 divided by pi. Get about -1.62. That's one value of t where the output of this function equals 10. Where is it in this picture? Evidently right there. That t coordinate is about -1.62. Looks about right, doesn't it? Looks reasonable. That's the t coordinate we just found by doing this work. If I had to find other t coordinates, use the picture to help you. For example, to find this t coordinate, use the fact that the period is 12. Take -1.62 and add 12 to it to get to the first coordinate of that point. What would it be? I guess it would be, I can do that in my head, 10.38. What about the first coordinate of this point? Well, these two numbers here and here are symmetric about this number, which is 9. And that distance is 1.38. So this distance has got to be 1.38. This would have to be 7.62 right there. Approximately. Got 2 minutes to talk about the inverse sine function a little more. And that's worth doing in 2 minutes. The sine function, as I drew for you earlier, looks like this. It's not a one-to-one function, and I drew it very poorly. It's not a one-to-one function. It fails the horizontal line test very badly. Infinitely many horizontal lines go through it infinitely often, not once. However, if we restrict the domain to just focusing on this piece of the sine function, what domain do we restrict it to? -pi/2 to +pi/2. negative 90 degrees to positive 90 degrees. That piece of the sine function is 1-to-1 and therefore has an inverse function whose graph is the reflection across the line y equals x. And where's my red? Whose graph is the reflection across y equals x, which looks about like this. And that means the graph of the inverse sine function looks about like this. It is an honest to goodness function that passes the vertical line test. Since the domain of the sine function we were considering is negative pi over 2 to positive pi over 2, the range of the inverse sine function is negative pi over 2 to positive pi over 2. Its domain is negative 1-to-1. Because the range of the original sine function is negative 1-to-1. Likewise, you can do similar things with cosine and inverse cosine and tangent and inverse tangent. Look at the problem-solving videos to find more examples on Moodle. Final 10-second comment. Inverse sine of something, t, is also called arc sine of that same thing. It's different notation for the same idea. This is more like inverse function notation. This is more just something different. This does not equal this. These are different. It's not a negative 1 power. It's inverse function notation. If you meant this, you would write this, or this, cosecant t, if you meant that. And these are not the same. Remember cosecant? Oh, probably not. There it is. Okay, that's the definition of cosecant, is the reciprocal of sine. Have a good day and a good weekend.